Assalamu alaikum everyone. This is lecture 18. We are going to start chapter 7, steady state errors. In the previous lectures, basically we have gone through the in this course. Actually, we are going through the design and analysis specifications. Those are actually three of the specifications. One of them is transient response. Okay, next one is stability. And the third one is the steady state error. Okay, so the transient response has already been discussed in chapter 4 and also will be discussed in detail in chapter 8. The stability is discussed in chapter 6. So now in this chapter, we are going to discuss the third specification, that is steady state error. So let's begin with the definition. The definition says that steady state error is the difference between the input and the output for a prescribed test input as t tends to infinity. So basically, difference between the input and the output for a prescribed test input. So the prescribed test input we already discussed in chapter 1. So basically here we are going to focus only 3 of them. Sometimes impulse as well, but in general, 3 of them are step. And the time domain is 1 and the Laplace domain is 1 by s. So this is your step, RT maybe. Then you have ramp. Okay, so time domain is t and Laplace domain is 1 by s square. And we also have the third one, that is the parabolic one. So this is t a half t squared, and this is 1 by s cube. As I already said in the chapter 1, that these are actually this represents position, this represents velocity, and this represents acceleration. Okay, so now the inputs we already defined. Sometimes also the impulse one is also unit impulse is also used as a prescribed test input. So whenever one of the 3 or 4 is been applied, then what is the difference between the input and the output as t tends to infinity? So just like a football match, what is the score at the end? So this is what we are trying to find out. But in control system perspective, t tends to infinity is actually means that whenever the transient actually dies out. Okay, so transient response is vanished, then what is the response? That is what is called steady state value. And that steady state, whenever we are obtain that steady state value, then the difference between the input and the output is basically our steady state error. So we can say that steady state error is basically the difference between the input, say in the Laplace domain we're writing. Actually, it will be more appropriate if you can write in the time domain. So RT minus CT, okay, and the limit is, time goes to infinity. So this is what is according to the definition, what is the steady state error. Now, since we are talking about three test input, the step, velocity, and acceleration, actually how they, in the physical, what is their physical meaning? Because you can see that velocity, the acceleration, or the ramp or parabolic one, they goes to infinity. So what is actually the significance of that, or what is the physical meaning of it? So for that, assume that we in the earth we have a satellite somewhere. Okay, so we have a satellite, something like this, and that satellite is actually tracking our a stationary. Okay, so stationary satellite is in the sky. So that stationary satellite is being monitored by this uh, tracking system in the Earth. Okay, so this is what we have. Now, this is what is called position, checking with the position. So this is also stationary, and this one is also stationary. So this is a physical significance of your step response. So at some point it is here, say, now your satellite is somewhere here. So now your Earth's position, the antenna should also be changing the direction so that it will be focused to that one. Okay, so this is for step response. Now, what about the acceleration? So now you have a satellite which is actually orbiting the Earth at a constant velocity. So now that one, so for that satellite, our tracking system always have to be changing with the same angular velocity as that one. So this is what is called your ramp signal or the velocity signal. Now, what about the acceleration? So for the acceleration, say we have a missile being launched, so which is now also having acceleration. So now our say tracking system in the Earth, it will has to monitor that satellite, that missile that is been left to go. So this is what is having the acceleration. So our movement of our tracking system has to be also accelerating. So how quickly it can track that acceleration. So this is the physical interpretation of your step velocity and the acceleration, or step uh, step ramp and your parabolic input. Okay, now, so what is the application of your steady state analysis? One thing you always have to be careful is whether the system is stable or not. So the first question is stability. Okay, so if the system is stable, only then we are going for the steady state error analysis. Otherwise, it doesn't make any difference for a unstable system. We are not saying that we cannot calculate the steady state error of an unstable system, but whatever the value you are going to get, numerical value, that will not be accurate. So this is why we also have to be careful about the type of the system. So we know the condition for the stability. The poles has to be on the left half plane. So if the poles are on the left half plane, then only we can actually apply our steady state analysis. So now the next is how to evaluate the steady state analysis. So say this is a step input. Our prescribed input is test input is basically prescribed test input is step one. So for the step one, we know that our output should be one. We're just assuming this is our one amplitude line. So now there is two possibility only. One possibility is after some time, when the transient is vanished, we'll be eventually merging with our input. So in this particular case, we are calling this one as a zero steady state error. So this is one output. The other one is after transient is vanished, we are always maintaining a same vertical distance. Okay, so this is what is called a constant steady state error. So one thing possible is zero steady state error. And the other thing possible for the step input is basically constant steady state error. What about the ramp one? So in case of ramp one, let's check what are the possibilities that we have. So so say this is your ramp signal. So one possibility is, so initially we have a deviation, then finally it may go and merge with the original input signal. So this is case one, which is zero steady state error. The next one, we have a deviation, then actually we have something like this, always maintaining a constant distance with this one. So basically a vertical distance which is constant. So this is your point two. We call it constant steady state error. And the third one is say we have something like this. So always maintaining a different slope. So basically it is always increasing. So one is going that way, the other one is going, so the distance is always increasing. So at steady state, it will be actually infinite. Okay, so they'll never actually be able to follow. This is a physical significance. So the output will never actually going to follow the input signal. So from the point of view of the steady state error. Similarly, for the parabolic one is also three possible. In fact, the higher the input from ramp on to onwards, it will be actually having the same. So either you have zero steady state error, or you can have constant steady state error, or you can have infinite steady state error. So something like this. So if this is your RAM signal, so either after some time you'll be merging, or you'll be maintaining a same distance, or you'll be maintaining a different always incremental distance. So three possibilities also there for your RAMs, parabolic signal. The next, before actually going into the derivation and how to apply those things, let us start with the sources of the steady state error. What are the reasons of having the steady state error? So sources of steady state error. So there is one common reason is actually nonlinear sources. Okay, so like we say the backlash in the gear or in the non-linearity in the motor. Okay, so dead zone we have in the motor. So all this kind of thing can actually cause the steady state error. So, but this is beyond the scope of this course, because we are going to discuss everything linear in this course. So that is why we're not going to discuss anything about the nonlinear sources. So there is another one that is called system configuration, and also the applied input. So the other one is system configuration. Okay. And third one is type of applied input. Okay, so this one is beyond our scope, and this one let us try to explain whether it will be understandable or not. Let's see. So say we have a unity feedback control system, and the forward path gain is K, forward path transfer function is K. So this is the scenario we have. Now, what is our steady state error? So by definition, the steady state error is the difference between the input and the output. So basically, this is where we are going to get our error. So steady state error is basically whenever the time is so high that our transient behavior is actually over, transient response is over. So at that point, what is the difference between the input and the output? So now in this particular case, as you can see that our error is definitely the distance difference between the RS and CS, no question. Now, what is our output CS? Output CS is actually multiplication of the gain with the error. So we want to have zero steady state error. That means the error should be zero. Input should be exactly following or tracking the output. The output should be exactly following or tracking the input. So in that case, this is what is desirable. Okay. So, but in this particular configuration, if you only have a gain as a forward path transfer function, so if your error is zero, your output is also zero. So for this configuration, you cannot have a zero steady state error, because as soon as the error is zero, your output will also become zero. So for this particular configuration, it is not possible to have zero steady state error. It will always give some steady state error. So, but you can actually change the value of the error. So since you need a specific output value, so if the value of the k is very, very high, then the error can be very, very low. So with high value of your gain, the error will be minimum, but it cannot be eliminated. So because of this system configuration, it will always be there. Now, what will happen if we introduce a different type of transfer function, say k by s. Now, 1 by s is basically, as we know, the integrator. So integrator can have an output even if there is no input. Okay, so let me mm, let me prove mathematically. So mathematically, d by dt of c, a constant value, is basically zero, isn't it? So differentiating the constant will give you zero, and inversely, integrating the zero will give us constant value. So because of this configuration, so even if the error is zero, still we can have some output. Okay, so physically, let me explain how it is going to happen. Like motor, we have given motor can be replaced here, and in the motor we have already given the command. Okay, so after giving the command, motor has rotated a certain angle. So it is still at that particular angle that we have obtained. And so the output is already there. So at that time, even if your input is zero, still your motor is going to settle for that particular position. So your output is already there, even if the input has been removed. Okay, so this is how system configuration can be one of the cause. And the third one, that is the type of the applied input. So we'll be discussing that one later on. Okay, so it's specific example, because before that we actually have to discuss few other theorem that we are going to use here. Okay, so it will be discussed later. Now, look at the theorem that we are going to apply. So for steady state error, we know that we are saying something like this. So steady state error E infinity is basically limit t tends to infinity RT minus CT. So this is what we are trying to say. Or if we know that this is our error signal, so we can also say that limit t tends to infinity, then this is your ET. Okay, so now because we are control engineer, we prefer, we can do this in this time domain, but in the time domain, the math calculation is a bit complicated. So as a control engineer, we actually prefer to go with the frequency domain analysis. So we'll try to transfer this thing into frequency domain. Okay, so in the frequency domain, actually we are going to take the help of the Laplace transformation of the derivative. So we know that the Laplace transformation of the derivative is from your chapter 2. You can see, we know that Laplace transformation of dft by dt. Say your time domain function is ft. So this is what we already know from the Laplace transformation chapter 2. S f of s minus f0. Okay. Now, so if you try to apply, this is already known, say this is 1. So you have to apply the actual Laplace transformation. So this is, say, sometimes this is also represented as f dot t. F dot t is nothing but d ft by dt. So we can just write it here as a notation. So if this is the case, then in the Laplace domain, 0 minus to infinity to f dot t e to the power minus st dt. Okay, so as t tends to infinity, so what will be the value of the s? S is the frequency, so f s will be actually tends to 0. So if you replace the s by 0, then actually this quantity will become 1. So what we have is 0 minus to infinity f dot t dt. So already f dot t is actually a derivative. So 0 minus to infinity, then dft by dt. Okay, so dt getting cancelled out. So now if you apply the limit, what is left is f, okay, so f infinity minus f0. Okay, so now compare these two equations. So equation 1 and 2. So from the equation 1 and 2, we can easily see that this quantity getting vanished. So we can say that f infinity, which is the last value or final value, or which can also be written as limit as, t tends to infinity, ft is equal to basically limit s tends to 0 s f of s. So this is the derivation of your final value theorem. So this is what is known as final value theorem. Okay, so we are taking the help of the final value theorem to find out the steady state error. So if we can find out our ET, or you can find out the ES in the Laplace domain. This is time domain, this is Laplace domain. So we can, if we can find out the ES, then in that case, our steady state error E infinity will be actually limit S tends to 0, S E of S. Okay, so but there is one thing we have to remember, that is to apply this steady state error analysis, as we already said, our system has to be stable. What does it mean? Is ES should have all poles in left half plane. Okay. If ES has poles in the right half plane, so your error analysis cannot be correct. So corrected value cannot be obtained. So basically you can apply, but you will give some error or the wrong values basically. So this is one thing we have to be careful about. So validity of your steady state error analysis if you want to apply the final value theorem. So let us now discuss few different scenarios. What is the final value actually we are going to obtain? Say that we have a stable system. Okay, so left half plane, stable system, left half plane poles we have. So basically the system is going to die out. Okay, so in that case, your final value will be 0. Now you have a pole at the origin. So you are having a step response will be approaching the value 1. So in that case, final value will be 1. So these two cases, this is all poles at left half plane, and if it is pole at the origin, and say we have right half plane poles. So in that case, can we apply what will be the final value? Can we figure out? So poles in right half plane. So this is what we have. So actually, final value will be infinity, infinite. So basically, we cannot rely on this case scenario. And the fourth case, say we have poles in the imaginary axis. So poles in the imaginary axis means you will have pure oscillation. So in that case, your final value is undefined. Okay, so poles on imaginary axis or j omega axis. Okay, so these two cases we can apply the final value theorem, and these two cases the final value theorem cannot be applied. Now let us elaborate the thing more specifically. So we have four regions. Say these are the four regions. One say that right half plane. Then say we have j omega axis without origin. We'll deal with the origin separately. So that is why we're just taking j omega axis without origin. This is your region 2. The third region is say left half plane, and the fourth one is the origin itself. So now let us look with the mathematical analysis, which one gives correct result, which one gives false result. So say first one, right half plane poles, or in this zone basically. So in this zone, we have definitely the system will be unstable, no question about it. And we are saying that from the graphically, this will be the case scenario, because you have some e to the power plus some value. Okay, so some real number maybe. So just assume any transfer function. Say that your transfer function e of s is 1 by s minus 2. Okay. So final value theorem, what it says, the final value theorem says that our final value will be limit s tends to 0 s e of s. So if you apply that, limit s tends to 0 s minus 2, so s is getting, so now we are going to get a 0. But is our final value 0? Our final value is basically infinite. So it doesn't say that you are not being able to calculate the value, but whatever the value you are going to calculate, that will not be correct. So you are going to get a wrong result. Okay, so this is a case 1. Now case 2. Case 2 is the j omega axis. So basically we're taking the j omega axis without the origin. So origin is left alone. So now, what about the system poles on imaginary axis? Imaginary axis. This is one thing. So system's behavior oscillatory. Okay. So graphically, what should be the response like? Response will be something like this. Okay. Now, or if you don't apply any step response, so maybe it will be oscillating around the zero value. Okay. Now, say your error is 1 by s square plus 4. So apply the final value theorem. So limit s tends to 0, s by s square plus 4. So 0 again. So basically it is giving you the mean value of the oscillation. Okay, but still, since it is oscillating in nature, so at any particular point, the steady state is not defined; is always getting changed. Okay, so that is why if this value is also wrong. Now let's consider the third scenario. The third scenario say that right half plane. So third one is sorry left half plane. So what's system behavior? Definitely stable. So graphically, it will die out. And as you can see, the final value will be 0. So let's try to use one example. Say to the power e of s is 1 by s plus 3. Okay, so your final value will be limit s tends to 0, s by s plus 3. So basically 0. So now it's giving you correct value. So it is always in the left half plane. If all the poles are in the left half plane, so your value is always 0. Now the last case, that is at the origin. So at the origin means actually a integrator. So integrator 1 by s. So if you apply an impulse response of the integrator, it will always be the integration of the input. So say your e of s is 1 by s. Now final value of this one is limit s tends to 0, s by s. So this is basically 1. So for an integrator or pole at the origin, so what we are going to get is something like this. Response is always going to get closer to 1. So one thing we have to be careful about. So if you have multiple pole at the origin, then what is going to happen? So we have to keep that thing also in mind. So if you have a multiple pole at the origin, say 2 of them, so in that case, this is the scenario. Now s is there, so 1 by 0. Now what you are going to get is infinity. So we have to be careful about the multiple pole at the origin. So the validity that we have said is that the poles has to be at the left half plane. All the poles has to be in the left half plane, as well as the condition should be at least at most one pole can be at the origin. If you have multiple pole at the origin, in that case, in this particular scenario, the output is going to infinite. So, so your final value theorem cannot be applied in that scenario. Okay, so and also one thing is very important, that is how many poles is at the origin. So this is also known as system type, but I will discuss this in the next lecture. So we are leaving that part. So multiple pole can be at the origin. So how to deal with those, we'll be discussing that later on. So what we are going to discuss next is that the point that the source, the third point of the source that we have left. So we can actually check that one. Okay, so this one, types of applied input. Say we have a system. Okay, 1 by s square plus s. Okay, so this is our system, and our input, say input is, okay, so our input, we are calling the input as delta input or impulse input. So basically the input is 1 and your output is C of S. Now, in this particular case, how many pole at the origin, that actually defines the system type. So just the definition, but more detail we'll be discussing later on. So type of the system, system 0, type 0 is if there is 0 pole at the origin. 0 pole at the origin. So type 1, if you have 1 pole at the origin, if type 2, if you have 2 pole at the origin. So this is how the system type is being defined. So in this particular case, we can see that we can take common of S. So basically we'll have 1 by S, S plus 1. Graphically, it means that we have a pole at the origin, we have a pole at -1. Now, in this particular case, what should be the final value? So the final value for this one is limit s tends to 0, s by s into s plus 1. So basically, it will be 1. Okay, so we can easily see this one is actually decaying response. This is the one that is forcing the value to be going to 1. So graphically, our response will be something like this. Now, if the input is being changed, now we apply a step input for this particular case. So what will be the change? So say this time RS is 1 by S. So what will be the response or final value then? So now this block will be slightly modified. Say we have something like this. Say we are having same input, that is RS. So RS equal to, still we are saying 1. So we're actually introducing 1 by S because of the step input. Then we have the transfer function 1 by S square plus S. So this one can be said here. We have the step one, step input. Now what will be our output? So what will be our output? Now, if we can find out the final value, will be basically limit S tends to 0, S into, okay, so also for the input we have another S. Okay, so S plus 1. Okay, so this is the system as well as the one that is for the step. So this one is getting cancelled out. So what is left is because of if you set S equal to 0 here, then 1 by 0. Okay, so infinite. So error is also because of the applied input. So if you apply for a type 1 system, if you apply a impulse input, then you're going to get the correct result. As you can see here, your the final value is 1. But if you are applying a different input like step input, in that particular case, we are going to see that our final value is becoming infinite. Okay. So this is what we have to be, which can also be another source of our steady state error. Now, finally, let us try to derive the steady state error. Okay. So one thing actually we are very, we already realized that for the step input, as you can see that in the formula we have a S times E of S. And also in the step response, the input is also having 1 by S. So this S and S is getting cancelled out. So if we know that the transfer function E of S equal to say some unknown value S cube plus 3 S square plus twice S plus 1 divided by 4 S to the power 4 plus 3 S cube plus 2s square plus 6. Okay, so for the step input, finding the steady state error is very, very simple because s and s is getting cancelled out. So you just replace the s by 0, and then your final value will be simply 1 by 6. So from this one, you can easily find out what will be our final value. Okay, so now for the step input, it is very, very simple. Now, in most of the cases, actually, we are not interested about the final value. Final value doesn't make much difference. So we are actually interested about how much we are able to track the input. So how much the input is being tracked by the output. This is a more important topic than actually what is the final value, as because of the fact that say a ramp input. Okay, so the final value is infinite, so it doesn't give us much information. Rather, if we can exactly follow the input, then our output will also be ramp, and also how accurately it is following, this is more important than what is our final value. So that is why steady state error is a better measure than actually what is our final value. Okay, so whether it has been able to follow the input or not, this is more important than what is the final value. Now, let us finally derive the steady state error. So say there is two ways we can derive the steady state error for the control system for unity feedback. So basically there is two broad ways. One is for unity feedback system. And the other one is non-unity feedback system. Okay, so we'll actually focus on the unity feedback system first. Then we'll use the same idea to derive for the non-unity feedback system, and it will be discussed at the end of the chapter. So now in this unity feedback system, we'll start with using two parameters. One is in terms of TS, which is closed loop transfer function. We'll be deriving in terms of closed loop transfer function, as well as in terms of G of S, that is open loop transfer function. Okay, so but I should remind you that this is more commonly used one, so we'll be preferring this one more than that one, but both of them can be used. So let us start with the first one using the TS. So for the TS, we know that RS is multiplied with TS will give us the output C of S. Okay, but at the same time, let me actually draw it downwards, then it will be easier. So C of S. But at the same time, error we are actually looking for. So error is basically RS minus CS. So yeah, you can introduce a summing junction here. So minus here, and bring it here. Then plus. So RS minus CS. So this is your E of S. So this is a block diagram representation for closed loop using the closed loop transfer function. which may be the method 1. Then we have the method 2. Actually, it will be better A, B. So say we are starting with A. Now, what is our error? Error is always same thing, ES equal to RS minus CS. And what is our output? Output CS is input RS into TS. So now you just put the value here. So RS minus RS TS. So it will give us ES equal to RS 1 minus TS. Okay, so now since we are applying the final value theorem, so E infinity or E steady state will be basically limit t tends to infinity et, or in terms of the frequency domain, so limit s tends to 0 e of s. So if you put the value here, so what we have is, so one thing we always have to be careful, sometimes I also forget, there is s star. Okay, so limit s tends to 0 s r of s into 1 minus t of s. Okay, so this is one way to figure it out. The other way is in terms of g of s. So let's go for that one. Say b is, so block diagram representation is the same as before, unity feedback system. So this is RS plus minus. This is actually our ES. And this is your CS. So if you want, you can actually rearrange the thing, because this is what should be our output this time, isn't it? So you can actually go with this one. So this is our output, E of S. It's always better to know how to rearrange the block diagrams. So it is actually coming from a summing junction. So we can actually draw a summing junction here. Okay, so summing junction, this is RS, and the other one has to be C of S. And then from the error, if you can multiply with G of S, then you are going to get C of S. So that is why you just can put the G of S here. So this is maybe a modified diagram, but it doesn't actually make much difference. You can also use this one. So bottom line, again, the error is the same thing, RS minus CS. And what is our C of S? You can easily figure it out from here. C of S is basically E of S into G of S. So RS minus E of S, G of S is your E of S. So now take the E of S in one side and take common. So E of S 1 plus G of S equal to R of S. So error is becoming RS by 1 plus G of S. So final value theorem will give us E infinity equal to limit t tends to infinity et, or in the Laplace domain or frequency domain, limit s tends to 0 s. Again, I forgot that. So you also try to recall this. Now, if you put the value of E of S, so then S R of S by 1 plus G of S. Okay, so this is the derivation for your steady state error in terms of G of S. Now, next thing that we are going to see for different type of input, how this error is going to behave. Okay, so say we have a step input. Before that, say that we have a generalized g of s. So say g of s is something like this. G of s equal to it has four zeros, so s plus z1, s plus z2 goes on. So similarly, it has pose s plus p1, s plus p2 goes on. So s to the power n. Okay, so this is what is very important here, s to the power n. N is actually number type. So if n equal to 0, that's equal, it's type 0 system, 0 pole at the origin, n equal to 1, type 1 system, 1 pole at the origin, n equal to 2, 2 pole at the origin. So this is what is called system type. Now, this is the generalized version of G of S. Let's say now we are applying step input. So step input for this version of E of S. Okay, so here, so see what happens. So step input is basically Rs equal to 1 by S. So our steady state error E infinity equal to, say we are applying for steps, so you can write step infinity equal to limit s tends to 0. The formula we have a s, rs is being replaced by 1 by s, then 1 plus g of s. So s is getting cancelled out. So what we have is limit s tends to 0, 1 by 1 plus g of s. So the rest of the thing is constant, only the limit can be applied to g of s. So we can write something like this, 1 by 1 plus limit s tends to 0, g of s. Okay. Now we already defined what is general version of G of S. So say G of S has no pole at the origin, then what will happen? So if G of S has no pole at the origin, so say n equal to 0, then limit s tends to 0, G of S, how it will behave? It will be actually, since this parameter is not available, so all the s's will be replaced by 0. So what will be having is 1 z1 z2 multiplied all of them divided by p1 p2, all of them are multiplied. Okay, so basically what does it means? A constant value. Okay, so if this is the case, then what should be our steady state error? So 1 by 1 plus a constant value will give you another constant value. So basically a finite steady state error we are going to get. Now what will happen if n equal to 1? So if n equal to 1, then limit s tends to 0, g of s. Now you have s here, then you have s plus p1, s plus p2 goes on. Similarly, s plus z1, s plus z2 goes on. Okay, so now because of this s, if you place s equal to 0, 1 by 0 is infinity. And if it is infinity, then your steady state error will be becoming 1 by 1 plus infinity is actually 0. Okay, so for n equal to 2, 3, 4, whatever it is, the number of the pole at the origin is increasing. So all of them will give you infinite. So your steady state error will be becoming 0 for rest of the higher system type. Okay, so for this is for your step input. Now what will happen for your ramp input? Now for the ramp input, what we have is okay, so ramp input. So basically now we have Rs equal to 1 by s square. So our steady state error is becoming E steady state equal to E ramp infinity equal to limit s tends to 0 s into 1 by s square. Rs is 1 by s square, so 1 plus g of s. So one is getting cancelled out, another is goes downwards. So limit s tends to 0, 1 by s plus s g of s. So if you apply the limit, this one will be 0. So the limit will be applied only to the s g of s. So 1 by limit s tends to 0 s g of s. So now your steady state error is modified for the ramp input to a form like this. Now again, g of s. So if g of s, from the general version again, if g of s n equal to 0, so then what will happen? Limit, there is no pole at the origin, so limit s tends to 0, s g of s, s g of s is something like this, s plus z1, s plus z2 goes on, and then s plus p1, s plus p2 goes on. So if you set the limit s equal to 0, so this function is becoming 0. So now your steady state error will be becoming 1 by 0 is equal to infinity. Okay, so this is for type 1 system. So sorry, type 0 system. Now for type 1 system n equal to 1, then limit s tends to 0. S, now we have 1 pole at the origin. S plus z1, s plus z2 goes on. Then s plus p1, s plus p2 goes on. Okay, now as you can see, this one is getting cancelled out. So now you will have z1, z2 goes on multiplication of all of them. p1, p2 goes on multiplication of all of them. So what you can see here is we are going to get a constant value. So your steady state error, will be 1 by a constant value is another constant value. So basically a finite value we are going to get. Okay, so next is n equal to 2. So for the next n equal to 2, s tends to 0. Now s by s square we have. So 1s is getting cancelled out. So 1 by s will be remaining, s equal to 0. That will give us 1 by 0 is infinite steady state error, infinite limit. So now your steady state error will become 1 by infinite equal to 0. So it's true for n equal to 3, 4, 5 because the pole at the origin increasing means the denominator will be always a function of s. So if you set the limit s equal to 0, it will be always 1 by 0 equal to infinity. So your steady state error will be 1 by infinity, always 0. So this is your for the ramp input. So as you can see, the pole at the origin has a very important function to play while we are calculating the steady state error of the system. Similarly, let's look at the example of your parabolic input. So parabolic input. So basically Rs equal to 1 by s cube. So our steady state error is limit s tends to 0, s by s cube, 1 by s cube, okay, y 1 plus g of s. So 1 is getting cancelled out. So still 2 s square is there. So 1 by, don't forget the limit, s tends to 0, s square plus s square g of s. Okay, so now if you apply the limit, this one will be 0. So what is left with is 1 by limit s tends to 0, s square g of s. Similarly, now if you apply n equal to 0 to this one, then what will happen? Limit s tends to 0. Basically, it will be helpful 0 and 1. So now, if there is no pole at the origin, then what will happen? S square is already there. So if in case of the 0, it will have s plus z1, s plus z2. Then you have s plus p1, s plus p2 goes on. So if s equal to 0 or 1, always this one will be dominant. So basically, the value will be 0. So your steady state error will be 1 by 0, that is infinite. Now, if n equal to 2, that limit s tends to 0, then s square will be cancelling s square. Okay, so what will be left is z1, z2 goes on, p1, p2 goes on. So basically a constant value. So your steady state will be also 1 by constant value is another constant value, finite value, okay? Another constant value. So what will happen if n equal to 3 or more? So 4, 5 goes on. So in that case, whatever we have higher order here. So now 1 by s will be there. So s is 0. So 1 by 0 is infinity. So your steady state error will be 1 by infinity is 0. So as you can see, for different values of your steady state errors, you can different input type, system type, we have a different steady state error. So this is how you actually have to calculate the steady state error based on the second formula, which is in terms of your G of S. So I think we already have already 1 hour is elapsed. So let me stop here. Continue from, I think we'll start with one example in the next class, example 7.2. See you in the next class, inshallah.